On behalf of the organizing committee for the University Distinguished Lecture, I welcome you all. So start first, we would like to I'm requesting our distinguished guest, Professor P. Ajayan, to come to the dais, please. And along with, I also would like to request our Registrar Sir, Dr. R. Prem Kumar, our Dean C. Sir, Dr. C. V. Tommy, our Dean Research, Professor Ranjit Thaba, please come onto the dais. I would like to request our Registrar Sir, Dr. R. Prem Kumar, to felicitate our distinguished guest, Professor Ajayan. Thank you. Okay. So now I would like to request our Dean Cs, Professor C.V. Tommy, to deliver the welcome address.
Good morning to all of you. A warm welcome for this University Distinguished Lecture. And with my privilege, I invite as well as welcome Dr. Ajayan for this particular talk. And VC sir also would have come here, but he has a little bit problem in walking, so he sends his apology for not attending, but as well as a warm welcome to you for this distinguished lecture. Anyway, you will get more information when our Dean Research is going to introduce the speaker. Uh, all we have to know is that he is a well-known scientist. Among the, typically we used to say that condensed matter physics. Now it has expanded to physics as well as material science, and holding many positions and active in research for a long time uh, for this particular area. So if you search for Nano, okay, his name will be the first one to come with maximum number of hits. So that many publications as well as activities he has taken over, and it is privilege for us to have him here and his talk. So welcome once again, sir, and I'll once again make sure that all of us are here. Whoever can come to this particular meeting, and thanks for coming.
Thank you so much, sir. So now it is my honor to introduce our distinguished guest, Professor Ajayan. Professor Ajayan earned his BTech in Metallurgical and Engineering from Benares Hindu University, and then he has done his PhD in Material Science and Engineering Department from Northwestern University in 1989. After that, he went to Japan, NEC Corporation for postdoctoral experience, and then he was a research scientist in Laboratoire de Physique des Solides Orsay, France. And after this, he did prestigious Alexander von Humboldt Fellow at the Max Planck Institute for Metallforschung, Stuttgart in Germany. Then in 1997, he joined the Material Science and Engineering faculty at Rensselaer Polytechnic Institute RPI as an assistant professor, and was become the chair professor in the engineering department until 2017. He left RPI and then he joined Mechanical Engineering and Material Science Department of Rice University as the Benjamin M. and Mary Greenwood Anderson Professor in Engineering from July 2007. From 2014, he is the founding chair for the new department at Rice University. The department name is Material Science and Nano-Engineering. Now, speaking about his research interest, Professor Ajayan's it includes synthesis and structure property relations of nanostructures and nanocomposites, material science and application of nanomaterials, energy storage, phase stability of nanosystems. He is one of the pioneer in the field of carbon nanotube. You can look through his Nature paper. He has published one book and more than 1,300 journals. And just day before yesterday, I was looking his H index. It is astounding 232,000, and his H index is 232. And he has given many lectures of different plenary and keynote lectures of various several international conferences in several countries. Now, speaking about his awards, Professor Ajayan received the awards from Spears Memorial Award by the Royal Society of Chemistry, UK, Senior Humboldt Prize, MRS Medal, Scientific American 50 Recognition, RPI Senior Research Award, the Barton Award from the Microscopy Society of America, and the Hadfield Medal for the Outstanding Student Metallurgist in India. He has been elected Fellow of the Royal Society of Chemistry, UK, AAAS, that is the Science Journal, Foreign Fellow of the Mexican Academy of Sciences, and National Academy of Sciences, India. and has been elected honorary member of the Material Research Society of India and the Indian Institute of Metals. He also received Distinguished Alumnus Award from his alma mater, that is BHU, Banaras Hindu University and Northwestern University. He has held distinguished guest professorships of many renowned international universities, for example, in School of Material Sciences at University of Louis Pasteur at Strasbourg and ISIS France, Tsinghua University, China, Shandong University, China, Shinshu University, Japan, Indian Institute of Science, Bangalore, Indian Institute of Technology, Madras, and NTU, Nanyang Technological University in Singapore. He received honorary doctorate degree from University Catholique de Leuven, Belgium in 2014. And in 2023, he has been elected as the Foreign Fellow of the Indian National Science Academy, that is INSA. And also, I mean, you already can guess that he is on the advisory editorial board of several material science and nanotechnology journal, high impact journal rather, and on the boards of several nanotech companies. Lastly, he has been part of two Guinness Book of World Records. One of them is the creation of smallest brush, and the other is for creating the darkest material. So we all are really eager to hear from him. So without further ado, I like to request Professor Ajayan to deliver his speech on nano-engineered material.
Well, thank you very much. Such a wonderful audience. Looks like a house full. And I'm very happy to be here. And thank you for the invitation. Ranjit, I think already had a very good feeling about how this place is. Met several of the young faculty. Looks like a very energetic and young set of faculty who will change the world, I hope, in the coming years. I'm going to talk about something very specific, although in our group we do a lot of different things. One thing that has been close to my heart has been this idea of engineering very small things, things that you cannot really see, you need a microscope to see. And how do you really engineer structures that small? In fact, structures that small has already been used widely. If you look at your semiconductor chip, the domain of size is already less than 10 nanometers. So we are already doing that. But again, as you push this limit to further and further, it's a challenging thing to do. And that's the essence of the message that I want to give today. And I'll pick up a few examples from many years of our work, some old, some new, to kind of demonstrate the complexity of this problem and the opportunities and challenges that exist in this. Of course, all this is possible because there are a large number of students and postdocs and researchers and collaborators who work together. Our group has been working with many folks around the world in trying to get some of these things done. And financial support from many agencies in the US and outside. And without this collaboration these days, nothing is really possible. Every published paper you see these days will have experimentalists, theorists, microscopists, synthesis people. And without this coming together of these people, it's very difficult to kind of accomplish the complex nature of the problem you're addressing. And I should mention that I've always had several Indian students in my group, almost more than half at any point of time, and from all over India. And I hope in the future we'll get some students from SRM as well. And one of the reasons for this visit is to kind of create this collaboration between the institutions, and hopefully we will have some formalized collaboration in the coming future. Now, when you talk about nano-engineering and nano-engineered materials, I can't think of a better material than what you're seeing here. It's a quintessential nano-engineered structure. In fact, 99 or more percentage of this material is calcium carbonate, which is a very brittle material. It's chalk, basically, right? You can break in your hand. But if you take this material, reduce it to the nano dimension, package it with the right kind of filler, in this case it is proteins, and sandwich it and create this brick and mortar kind of architecture, you get a material that is super tough and super strong. You cannot break a shell in your hand, all right? But you can easily break a piece of chalk. So that is really the ultimate result of nano engineering. And of course, nature has perfected this over millions and millions of years through trial and error approach and really bottom-up assembly of materials that is available in nature to that environment. Right? Nature has done amazing things in this nano engineering area. Another example would be a bone, right? Again, very similar thing. A ceramic and an organic matter put together, engineered at the nanoscale, to really create an outstandingly tough and resilient material. So this approach, the question is how well you can do in the lab, and this has been the question asked by many over the years. And it's not very simple at all because of the problem of the interface. Everything when you think about structures like this, it's all about the interface. You have two different materials, and how do you put these things together really matters how the ultimate structure is going to come out. So the interfacial engineering is what really nano engineering is. And that you will realize it with many of the examples that I'm going to give you. Coming from the biological structure that I showed you to the kind of structures that we want to build in a synthetic world, it looks something like this. You have all these bits and pieces that we have really mastered in creating, all the way from nanomaterials, 2D structures, carbon nanotubes, and how do you really create all these things into a functional architecture? And that's really the crux of the challenge. And again, it comes out to be an interfacial problem. How do you really bring together different dimensionalities, different sizes, different compositions, and ultimately create this connectivity, right? That's really an interesting part. So let me start with this one particular type of material which is close to my heart, and where we started in terms of the nano revolution. In fact, the nanotechnology was initiated in maybe late 80s or early 90s, and it became a big deal because ultimately there was even an initiative from the US government to really promote this technology. And it all started somewhere, in terms of materials and how people realized that you can make very small scale structures and explore the properties and realize that they are much better than the bulk materials in many ways. So carbon had a great place in that whole story. And of course, it was, the initial discovery was the discovery of what people call the fullerenes or buckyballs. And it happened at Rice University, where I'm right now from. Even before I joined Rice, the three folks who came together, again, two from Rice and two from England, to create this major discovery, which initiated the nanotechnology revolution in many ways. And again, one has to think about this whole scenario. Pure carbon, just a simple element carbon, can come together in beautiful ways to create amazing properties. So the fullerene discovery started, then it was followed up after many years with the carbon nanotubes, which I'll mention a few more things. And then maybe a decade later came out with the graphene discovery. And two of these discoveries already received the Nobel Prize. Fullerenes received the Nobel Prize in '95, and in early 2000, the graphene discovery received the Nobel Prize. But if you think about these three structures, it's kind of remarkable because the graphene, which was discovered latest, the last, it's essentially a building block of graphite, which is a commonplace material. Graphite, many people have been using for centuries. It's a practically very useful material. And graphite is made of these stacks of graphene. You can, in fact, peel off graphite, very thin layers of graphene. They stack up to make graphite, so easily peelable. And that's how the Scotch tape method that ended up in discovering the graphene material. But again, this whole story has something to tell, because ideally, intuitively, one would have imagined that graphene would be the first thing to be discovered because it was already there, right? But the whole thing started with fullerenes, which is probably the most complex of these three structures. And then came the carbon nanotube and then graphene. So again, this tells that discoveries are almost always serendipity. Right? So, there's no real uh, uh, pathway for, discoveries, big discoveries that happens, right? So again, it is something to tell. Creativity, imagination, these are the fundamental attributes of discoveries, and this is a great story to tell in that perspective. But in any case, I won't say much about the C60, but I'll talk a little bit about carbon nanotubes because that's where I started my research journey. And then we will go to some other examples that are more recent. Now, when the carbon nanotubes were discovered in the early 1990s, 1991 to be precise, people thought they have discovered the strongest fiber. And every theoretical calculations and everything that is about this nanotube structure, perfect structure made of this hexagonal honeycomb carbon lattice, that is the graphene structure, rolled up into a cylinder. Everybody from every point of view said that this is the ultimate fiber, right? You have the highest mechanical strength, you have the highest electrical conductivity. So the question was, how do you really translate this beautiful building block that is a small tube that is almost as perfect as you can get with no defects into a practically relevant material, right? So that was, that kind of is the context in this whole nano engineering talk that I'm going to give. So the only issue with carbon nanotube is it's too tiny, right? It's about 1 or 2 nanometers in diameter and maybe microns long. But you can't really use a nanotube that is a few microns long as a fiber for any practical applications. So in order to get to that point where you can actually use this nanotube building blocks into a fiber, you need to put them together. You need to engineer them into a real fiber that you can practically use, like a carbon fiber. Now, it has taken almost 30 years, and we still don't have a fiber that is as good as the present carbon fiber, which is made by extrusion and so on, right? So this is again the challenge that in the nano engineering world. And the reason why, again, I bring this interface problem is when you put 2 nanotubes together, then there is an interface which is very weak. And finally, the product that you create is dominated by this interface. Of course, there are various ways to solve this problem and various ways to kind of create this in a seamless way. But still, the challenge is severe, and it's taken so long to get to the point that you're seeing today. It's actually a colleague in the background, Professor Matteo Pasquale, who actually spins these nanotube fibers continuously in his lab. And again, as I mentioned, the properties are still not good enough to compete with the existing highest carbon fiber. But there will be a point where you are going to compete with these materials, and then you have a revolutionary technology. So all the way from the building blocks of nanoscale to the actual product that will ultimately change the world is a long pathway. That's a message that I want to give. And if you have a carbon fiber that is much better than what you have today, then technology will be hugely impacted. The highest conducting fiber, maybe perhaps one day you can replace the metallic wires that you use for transmission and so on, right? And carbon is much better than metals because it doesn't corrode, it is light, all kinds of advantages. And if you have a very strong fiber, it is much lighter than the carbon fibers because the density is much lower. You can actually use it for space applications and so on, right? So people envision this product, envision the applications, but it took a long time in terms of the engineering part to get to where you want to be. Now, there is another aspect of things like carbon nanotubes. They're very interesting electronically because by simply changing the twist in the lattice of carbon nanotube, you can go from metallic to semiconducting and so on. But then again, it was a problem because when you manufacture these materials, you get a mixture of all these electronic properties, and you have to sort out semiconducting and metallic materials later on. And it has again taken a very long time. And today we can actually get highly pure nanotubes, purely metallic nanotubes with a specific chirality, which is again the twist that I mentioned. Or you can get semiconducting nanotubes. Not only that you can get these pure nanotubes that is sorted from what you manufacture, you can also align them in unidirectionally. So the particular paper that you're seeing is about creating a membrane that consists of a specific type of semiconducting nanotubes that are all aligned in one direction. And again, it's the nano engineering that I'm talking about, going from a simple technique that can produce large amount of this material to actually getting a specific type of structure all organized and aligned in particular way, that gives you a product that can really change many technologies. This particular aligned nanotube film can have optoelectronic properties, chirality selection, all kinds of beautiful properties. So again, it is a good example to show how much time it takes to actually get to a high value product from these nanoscale building blocks. So that was kind of the preface of my talk, just to give you an example of some of the things that we did early on in terms of nanotubes and other carbon-based materials to be able to get to a point where you can say you have a real nanotechnology product. And of course, carbon has been dear to us. We still work on carbon. We are now starting to look at a diamond, which is really a fascinating material. We actually grow single crystal diamond, not for the jewelry that people think about, but actually for electronics. Diamond is going to be a next big candidate for high power electronics. It's material science has really progressed to a point where things unbelievable can happen. And today we are thinking about real large scale wafer sized diamond crystals. Again, that's a different technology I will not talk about, but just to give you an example of how things can move and driven by technologies of interest. So today in my talk, these will be the 3 talking points, and depending on the time, I will skip a few things along the way. First, I will talk about these atomically thin materials that came out after the graphene discovery. Again, as I said, graphene discovery happened in a strange way. People are scotch tape peeling graphite and getting thin layers, and they found some beautiful physics. So that kind of evolved into a lot more different compositions of materials that have similar thicknesses. So you're looking at materials that are just a single atom thick or a single unit cell thick. Imagine how thin that is. And imagine that you're able to make a very large wafer, centimeters or inches large, with just single atom thick. And you can do that very, very well today. So that's one kind of material or one example that I will mention. And then people are actually even pushing the limits to being able to manipulate single atoms for things like catalysis and things like that. So that's again, an amazing technology in areas like catalysis and so on, which will have a huge impact. And then finally, I will mention about a particular kind of technology, a particular type of process, which is actually bottom-up, hierarchical process that allows you to create complex architectures, and that is printing technology. Of course, 3D printing or additive manufacturing people talk about. There are many variations of that theme, but people are pushing the limits of this technology so that you can actually create complex architectures with nanoscale precision. So these are the 2 examples that I will give. But again, as I said, we work on many things application-wise and materials-wise. But this kind of gives you the whole story that I want to talk about in terms of the nano-engineering. So from graphene, as I said, people expanded to many other compositions. And here are some of the examples of the compositions that people have been looking at in our group. We have been looking at all the way in terms of electronic properties of metallic to superconducting. So all kinds of compositions are available. People can actually scalably create many of these materials. They have single unit, lattice unit thickness, and they can make it in a pretty large area system, which is important for applications. Now, of course, there are many drivers to create or to build or to synthesize these type of materials. And one of the drivers is, of course, semiconductors. Semiconductor technology has been always looking for alternatives in the future. Silicon has ruled for a very long time, and there will be a transition from silicon to something else, because with the same kind of technologies, you really cannot deal with the power situation. There's a limit to how much silicon can scale down, and at some point of time, the power requirements go up, and power is now everything in terms of computing. Because all this AI machine learning, the biggest challenge is the actual power taken by these type of computing problems. So there has to be an alternative. There has to be a change at some point. I don't know how long it's going to take, but definitely. So people have been looking at various alternatives to things like silicon, or not just material, but also the architectures. Today's most prominent semiconductor technology is the FinFET. It's almost a 3D technology based on similar kind of material, but rather than lateral, you go vertical. And again, this is an interesting paper from a friend of mine, Kausal Banerjee, from University of California, Santa Barbara, trying to kind of summarize the comparisons of the possible materials that might change in the future. And this is not just to do with the materials itself, but also the interfaces, the integration, all kinds of problems are factored in. And they come up with two alternatives. One is the single wall nanotubes that I already mentioned, and the 2D materials options. Both are semiconductor materials. Both have had about 20, 30 years of development. So there is a potential that these materials might be the next generation for computing. Of course, there are many, many challenges in each of these. If in either of these nanotubes or 2D materials, the thermal budgets are problems, the integration is problem, interfaces could be problem, contacts could be problem. But anyway, in terms of the metrics that define the high performance semiconductors, these certainly come out as potential candidates. So again, we'll have to see how that works. So one of those candidates I'm going to pick up and talk about, which is the 2D materials, graphene, boron nitride, a very similar single atom thick material, or transition metal dichalcogenides, TMDs. These are interesting semiconductor materials which can also be peeled off like graphene, and you can actually make these single unit thick material over a large area. So last 20 years have seen incredible amount of work in trying to controllably make these materials like TMDs, the transition metal dichalcogenides. These are typically materials like molybdenum disulfide or tungsten disulfide. They are again van der Waals, which means that they have these strong layers that are stacked together with weak forces so that you can easily peel off, or you can actually grow these single unit thick material. We were, in fact, one of the early groups that started to pioneer this vapor phase growth of these type of materials in the early 2010s. Now, when you're trying to grow such materials, there are also some challenges because many of these materials exist in multiple phases. When we talked about nanotubes, we said there are metallic nanotubes, there are semiconducting nanotubes. It's a very similar story here. And because they are going to the atomically thin regime, it can very easily change the structure, maybe distortions and things like that, and that can easily change the phase. It's not necessarily the dichalcogenides, but also dioxides, things like molybdenum dioxide can exist in multiple phases. It can be metallic, it can be semiconducting. So when you grow these materials, you have to worry about how you can control specific type of phases. The reason why I just showed you is because later on, I'll talk about some lateral junctions, heterostructures, where these phase engineering is also quite important. And then you can also have multi-compositions, multiple components in these systems. You can have alloys, for example. So this is a very interesting material that we made in our lab that has 4 components: molybdenum, tungsten, sulfur, selenium. And they are very similar as they mix pretty well. And you can see on the right-hand side, this atomically thin layer that is imaged with atomic resolution. And one thing I want to point out is that with all these new technologies and materials coming up, you also need the right tools to analyze them. That beautiful image is a scanning transmission electron microscopy image of a one layer of this 4-component system. You can image every atom in position. Not only every atom, you can even look at the composition of every atom, right? So today's microscopy and spectroscopy techniques are so powerful that they can actually get information at the single atom scale, which is also important as you're trying to engineer every atom in the system as you go along, right? So I think these type of structures not only need to be controllably synthesized, but also understood from a metrology point of view. So I just wanted to give you some impressions of how these kind of materials look like. But what I want to really talk about is this engineering aspect. Let's say you had the building block that was carbon nanotube, and I mentioned about the difficulty in actually creating this fiber from these nanotubes. But here you have a different types of structure, again, nanoscale in thickness, right? Single unit thick, maybe just about a nanometer. And how do you really engineer these structures? Now, when you come to this 2D layers, it's very, very interesting because you can stack them, right? Because they are well bonded in the plane and they are weakly bonded off plane. So you can actually put them together in stacks. So when you think about stacking is an interesting problem. It's an interesting engineering approach. The good analogy will be I take two decks of cards and shuffle them, right? And if I have different compositions, I can do the same thing, but each card would be at the atomic scale thickness, right? So by stacking these or shuffling these, I can get these heterostructures with different compositions. So the picture that you're seeing here is precisely that, right? I'm able to make all these 2D atomically thin layers, and I'm going to put them together. I'm going to stack them, and so on and so forth. And of course, when you stack them, there are complications. It's not like shuffling two deck of cards, because now here we are talking about atomic lattices that you are aligning, right, when you stack. So first of all, there are different phases to these layers that you have to control. Secondly, you have the stacking problem, right, as I call it. Stacking problem is, again, the alignment between the two layers. See, in a typical situation, when you have a macro scale layer, the stacking order doesn't really matter, right? Because everything averages out. But when things are at the atomic scale or single atom thick and so on, then the interaction is much, much stronger, right? The overlap of electron orbitals could be much stronger, right? So when you stack two layers together, the actual orientation between the layers also becomes a big deal, right? In any case, even if you're going to stack, it will be quite challenging to kind of build a stack of certain thickness because each one is only a single atom thick, right? I can imagine creating a stack by picking and placing every layer, right? But how long will it take to create a 5 nanometer stack? And it's also, there are other practical challenges in doing that. So one thing we were interested in doing from the beginning was to be able to create these stacks in one shot. So introduce all the precursors to grow. Again, we do a lot of vapor phase growth, and together they grow. And depending on the phase stabilities and phase diagrams, you could find a condition where they actually separate completely, segregate, right? So that might be one way of doing this. Again, it's a lot of trial and error and optimization. And today, people are actually trying to do this in a more controlled, rational way to be able to create the exact stack that you need. But in this particular case, I'm looking at two materials, molybdenum sulfide and tungsten sulfide. Both are atomically thin layers. And how do you really create a stack together? And again, from a materials point of view, material science point of view, it's very fascinating because by doing this stacking business and in a combinatorial way, you can create a whole range of new material systems, right? I mean, people knew there was molybdenum sulfide, people knew there was tungsten sulfide, but nobody really made a moly sulfide, tungsten sulfide stack. And you can think about a whole range of opportunities in doing this. And that's why from people like us who did material science, this is really fascinating. And then to understand the properties, then to control the phases, then to control the twisting, right? All kinds of interesting things. And again, you'll be seeing a bunch of images. You don't have to really worry about the details. But what was possible from our experiments in the early days was that we are able to lock in a certain type of stacking. We were able to create certain type of stacking in a certain window of growth synthesis parameters. So that was very good. At least we can create a heterostructure with a particular type of stacking, with a particular type of composition. And then came this whole creative approach where they were really trying to twist the layers once you stack. There's a whole area that has emerged called twistronics, and I'm sure many of the audience here who has been working in this area knows about this. And the idea of twistronics is because the layers are atomically thin, and if you can control the stacking order between the two layers, then you can get specific type of electronic structure of these stacks. People have found superconductivity in a bilayer stack graphene. People have found exotic optical properties when you stack at a certain angle. So twistronics has become really a tool in engineering. You wouldn't typically imagine that twisting two, films would be called engineering, right? But when it is in the atomic scale, when the thicknesses are in the atomic scale, then you start to see significant changes in the electronic structure and physical properties by just twisting. Now, practically, it is a very challenging problem. How do you really twist at a certain angle when you have two layers that are atomically thin? Now there are robotic ways of doing this. People actually manage to twist exactly a certain angle called magic angle, which will have a really interesting behavior. So again, the difference between typical engineering as we see it and engineering at the nanoscale is quite different. You're really doing things at the atomic scale. Small twists have a large impact in the behavior. A small chirality change in nanotubes have a huge impact in electronic structure. So that's the whole flavor of nano engineering that I want to convey. But today, by twisting, essentially what you're creating is this moire patterns and slightly different interaction of the electrons in either of the layers and very different properties. So by twisting, people have figured out all kinds of ways to get interesting ways to control excitons, create superconductivity, all kinds of things like that. There is another option, and that involves a little bit of chemistry. And that is by taking layers of different kinds and hybridizing them. By hybridizing, I mean electron transfer, right? In the previous example, the twisting, there were two van der Waals layers where there was not so much interaction. The strength of interaction is, of course, important. So we started to do things that are slightly out of this simple twisting business. In this particular case, we decided we'll take a layer of one kind and a layer of a very different kind so that there can be electron transfer between them, some kind of loose bonding between the layers. And that gives you interesting heterostructures as well. So in this particular case, we use a layer of silica or glass. Glass, as you know, it is a three-dimensional structure, but people have figured out ways of creating almost 2D glass. And that's a very fundamental problem which people have still not solved. Can a glassy structure exist in 2 dimensions? But we were not really deep physicists, so we are more interested in trying to figure out what kind of heterostructures we can make. So let's say you are able to make 2D silica, and then you take graphene and then put them together, and you have a very different kind of architecture. In fact, this combination of graphene and silica, we call it graphene, right? Glass and graphene. And basically, it's a single material because there is electron transfer and there is hybridization between the two layers, right? In fact, we did a lot of experiments. Actually, you can make these hybrid silica graphene layer by vapor phase deposition of using a particular precursor, the single step method. I'll quickly go. But again, by looking at the phonon modes that are in the structure, and also detailed Raman spectroscopy and IR spectroscopy and so on, basically, we have proven that this is actually a unit that is different from both graphene and silica, right? And one could think about all kinds of hybridization that you can build from materials of such different nature. I can hybridize an insulating material and a conducting material to get something in between. In fact, in this particular case, it seems to be a semiconductor. You can use techniques like reels and UPS to actually get information about the band gap. And in this particular case, the band gap comes out to be 3.6 eV, which is a wide band gap material. So again, it's another kind of engineering. Introduce this simple stacking approach, simple twisting approach to some chemistry. Whenever I say chemistry, it means electron transfer. Right. So that's a fascinating material that we have been playing around in recent times. And if you go in the vertical direction, there is another additional thing that you can do for these type of 2D materials, and that is intercalation. The whole world works on intercalation. I don't know if you know, because all the electrodes in your batteries work on intercalation. right? Lithium intercalates into graphite and reintercalates. That's how you provide the energy, you get the energy, right? So intercalation is a very beautiful approach to create all kinds of interesting systems. And we also tried intercalation in many of these 2D stacks. And in some cases, you can disrupt the properties significantly. You can actually get to different conductivities and so on and so forth. So that's another way to engineer. You insert some elements in between the layers that you're stacking, right? So again, these are typical ways you can manipulate these type of building blocks. In this, I'm mostly focused here on 2D materials, but nanostructures in general, they're amenable to all these different type of manipulations that allows you to engineer these structures to get things of various physical properties. And this question about growing large stacks is always complicated. In fact, we have tried to grow multi-layer stacks of these different composition material. But again, under certain conditions, you can create these nicely separated layers, but in some cases, you start to see alloying, you start to see different type of architectures. So again, growing these consistently and controllably is really quite challenging. Now, let me talk about a different kind of heterostructure, different kind of engineering. Now, most of the things that I mentioned so far has been on taking these layers and putting on top of these and vertically stacking. But you can also imagine that you start to change the structure within the plane, within the layer, right? I can create different compositions locally on a single layer, or I can create defects locally in a single layer. And those would be electronically different, topologically similar, but electronically different. So this lateral structures, lateral heterojunctions were also very interesting. In fact, the first experiment we did in this was much simpler. We took a graphene oxide layer, which is basically oxidized graphite, and then made a thicker film, and then locally changed the oxidation, in the regions by using laser beam. So basically laser patterning, right? Go across the film and essentially reduce locally the graphene oxide into reduced graphene oxide. So you have a contiguous film, but regions that were reduced were conducting, because when graphite gets oxidized and you make graphite oxide, it is becoming less conducting and more insulating. So those regions of GO were used as electrolytes, and the regions that were reduced were used as electrodes. So you could actually build an entire device by simply laser patterning this graphene oxide film. It was, it was a supercapacitor, and by adding some electrolytes into the graphene oxide, you could use them as an efficient separator plus electrolyte. So you can get a very thin film supercapacitor device by simply taking a geofilm and locally patterning it. And this is the importance of this lateral junctions. Now, if you think about lateral junctions, and if you go all the way to the atomically thin regime, what kind of lateral structures can you make? And one great example of this was boron, nitrogen, and carbon, the phases that consist of three components, boron, nitrogen, and carbon. This particular phase has been of interest to us for a very long time, the compositions that contain three elements, boron, carbon, and nitrogen. And if you think about these three elements, they are abundant, they are light, easy to get, right? There's no metals or things like that that oftentimes are considered as critical in here, right? And these three components combine to form very many absolutely interesting materials. Now, carbon, if you take a single component, carbon, you already know, graphite, graphene, diamond, all these elements also exist in cubic form. So hexagonal, which gives you this 2D layer, cubic, which gives you the three-dimensional layer. So carbon has the variety, right? You have the graphite and you have diamond. Boron nitride, the two-component system, is also very interesting. It also has the hexagonal form and it has the cubic form. In fact, the cubic form is very difficult to make, and we are actually have a project in trying to do that. So cubic boron nitride is also possible, right? There's carbon nitrides, which are catalytically very interesting for nitrogen-doped carbons, right? So those are fascinating. They also exist in hexagonal and cubic form. And then there are also the three-component system, the boron, carbon, nitrogen systems. There are compositions like BCN, there are compositions like BC2N, BC3. There are many, many compositions, right? And some of them are semiconductors, some of them are metallic, and they are all single atom thick. If you think about it, the truly single atom thick material is essentially graphene or boron nitride, right? The other molybdenum sulfides and all have essentially slightly thicker, unit thickness. But anyway, we were fascinated by this three-component system: boron, carbon, and nitrogen. And we wanted to actually make, because people had already made graphene, people had already made boron nitride. We actually wanted to see if you could make a BCN three-component system in a single atom thick layer. So we essentially did that experiment, did vapor phase synthesis with precursors containing boron, nitrogen, and carbon. And instead of forming this thermodynamic phase, that is BCN, what we actually got was a mixture of phases, boron, nitride, and carbon. The boron and nitrogen atoms tend to come together, and carbon tends to come together, and they form these patchwork, essentially a quilt-like architecture. Again, all in a single layer. So you can see this is exactly what we got. Instead of getting a uniform BCN phase, we got boron nitride domains and carbon domains. But because they are isostructural, because the lattice parameter is almost the same, they get nicely stitched together at the edges, right? So you have a single atom thin layer with domains, nanoscale domains of boron nitride and carbon stitched together throughout, almost dispersed throughout, depending on the composition that you use and so on. So that was interesting. This is the first time anyone has actually seen that you can actually create a lateral heterostructure in a single atomically thin layer. There are a bunch of things about boron nitride. I'll skip these. A very interesting material. You can grow over different materials. It's also a very unreactive material. People use boron nitride for oxidation resistance, coating on metals, and so on and so forth. And again, those were some of the things that we did early on. There are many other applications for these. You can coat boron nitride on metals to get more stability for electrodes, and so on and so forth. But anyway, let me get to the point that I'm trying to make, and that is this idea that you can laterally engineer domains of boron nitride and graphene, same structure, same thickness, same lattice parameter, into a seamless junctions, right? And once we actually saw that, we devised some techniques to actually do this in a much more controlled manner. So you can see that you can create engineered domains of boron nitride in graphene or graphene in boron nitride, which gives you all kinds of possibilities on a single atom thick layer, right? You essentially can, for example, put a pattern of graphene in a boron nitride lattice, and you use that as an antenna. So once you actually grow that, you can actually peel the single atom layer and put it on other structures and so on and so forth. So this is really engineering at the scale of a single atom, right? Thickness. So you can create all these beautiful structures. Of course, the owl is actually a rice mascot. That's why we always use owl. And you can also start, once we realize that you can do this with boron nitride and graphene, which is really an interesting system because graphene is conducting a metal. Boron nitride is actually an insulator. So imagine at a single atom thick level, you are joining these insulating material and conducting material in plane laterally. Then we also started to think that there are many materials that are isostructural. Even in the tungsten sulfide, molybdenum sulfide material that we saw, we could create the same kind of heterostructures laterally. And again, these are two different compositions, but same structure. The band gap is probably very similar, but not exactly the same. So we started to make these type of nanostructures as well. So you can see that beautiful atomically sharp interface that is created from combining two different materials, that is tungsten sulfide and molybdenum sulfide, in a single atom thick layer. Now, what is interesting about this is the interface between these two different materials is sometimes not very stable. You can imagine, right? Now you're thinking about materials that are essentially made of surfaces only. So diffusion and other kind of mechanisms can be very prominent here. So you can actually see some of the atoms from this side has ended up in the other side, right? Because the diffusion of atoms can be actually visualized in the TEM. In fact, the stability of these type of structures are fascinating from a materials point of view. In fact, we have done many experiments to see how the structures go from unstable to stable states. So, for example, if you have these lateral junctions, you can heat it and they could actually start to mix at some point in temperature. And you can actually monitor this in situ in a TEM to see how the atoms are actually moving around and how the atoms are actually can be controlled. So again, this is somehow the kind of things that are important to be able to create these heterostructures, and also to control the mobility of atoms, to understand the mobility of atoms in these type of systems. Now, I mentioned about two different scenarios when you talk about lateral junctions. I talked about a metal insulator system, boron nitride and graphene. I talked about two semiconductors joined together, right? Different band gaps, tungsten sulfide, molybdenum sulfide with different compositions. I can also think about the same composition, but different faces. Initially I started to say that the same material can have different faces. So this is an interesting material, molybdenum ditelluride, which exists in two different crystallographic phases. And I could also engineer these phases in a single atom layer in the plane. So again, molybdenum telluride exists in 1t prime phase, which is metal, and 2h phase, which is semiconductor. So I could, again, using this idea of engineering, create these lateral junctions, periodically repeating lateral junctions with two different phases of the same composition, right? And that essentially gives us to the real exciting phase of this whole engineering in lateral dimension. And that is the idea that you can create these domains of very different electronic structure adjoined to each other and create all kinds of quantum states in these. So if I look at the transition metal dichalcogenides, they exist in different phases, and some of these phases are called trivial because they are semiconductors, and some of them have these quantum mechanical effects, and they have they call it topological materials. Again, several of the physics folks here might know what these structures are, and the possibility of combining them and putting them next to each other in close proximity in a single layer material gives you fascinating opportunities to kind of play around in the quantum regime. So that was what was interesting. And I'll show you one example, which is mostly done in Berkeley, but we were collaborators, that suggests the scalability of this approach, right? So most of the structures that you saw, these laterally distributed domains, were done by vapor phase techniques. But you could also create these layers and then locally go and change the layer in specific locations. So in this particular case, we actually grew these layers, let's say tungsten selenide or something like that, and then using electron beam or focused ion beam, go locally and create defects in these systems. And once you have defects, you can actually introduce another element and change the composition locally in those places. So for example, if I take tungsten selenide, I can remove some selenium from locations, and I can reintroduce sulfur in those locations. So essentially, I can use this 2D layer as some kind of a platform or some kind of a canvas to really start to paint different domains or different crystals, structures, and obviously properties, right? So this is actually a beautiful image that was done through, again, the patterns were using this Armenian god. That figure itself is a hybrid, actually. You have a face of a man, body of a lion, and wings of a bird. And essentially, you use this canvas to actually create the patterns that I was just talking to you about. You locally change and create pixelated structures, right, in 2D. In fact, almost like a checkerboard pattern, right? And again, these pixels are optically different because they're electronically different, right? So you can get all kinds of beautiful photoluminescence and stuff like that from these locations. So you can essentially build whatever you want, the images or the optics that you want by using engineering approach to this canvas, which is essentially an atomically thin layer, right? So that's kind of the engineering that we are talking about. I don't know how much time do I have left. Just tell me what is the time now? Okay. All right. right? So I'll probably spend a little bit of time quickly on some of the other kind of engineering that we are interested in. And this is related to defect engineering and single atom engineering. And this is particularly interesting for catalysis and things like that. Of course, today people also talk about single photon emission from certain materials, of course, defects are important in these. But we have done a few things, and I'll give you a couple of examples before I go to the last section. So again, using carbon as a platform, you can start to insert other elements into the carbon lattice. You've already probably heard of NV type of defects in diamond, right? It's very important for quantum computing. But in here, you have hexagonal carbons, graphene and graphite, and you start to replace some of the carbon atoms with nitrogen, phosphorus, boron, and those now become catalytically very active. Now, the nitrogen-doped carbons are very important. Huge amounts of work has gone in by many groups around the world in trying to see if you can replace traditional catalysts like platinum, which is expensive and rare, with the carbon nitrides. Again, platinum is used as a catalyst for many, many applications, and it's not an easy material, and it's expensive. So the carbon-based catalysts have become very popular. So we have been playing around with nitrogen doping, single nitrogen atoms in carbon. It's not very simple, it's complicated depending on exact positions that nitrogen takes in these graphene lattices. But nevertheless, you can get catalytic activity from these. This is an example of a CO2 reduction, which is again an important technology that's emerging. For carbon dioxide reduction, actually the only catalyst that is really reasonably good is copper, and copper has its own challenges. So many folks are now trying to figure out how to use nitrogenated carbons for CO2 reduction. Again, in catalysis, the actual active catalyst and the support systems are equally important. So we have also been playing around with the support. So in this particular case, the carbon support is highly curved, and that gives you certain kind of fields that allows better efficiency in catalysis. Again, if I put single metal atoms in these carbon supports, you get much more efficiency in the catalysis, like hydrogen evolution reaction. And then the other challenge or emerging field is actually to be controllably placing single atoms of any particular kind in the host lattice. So again, this is not just from our group, but many groups today are trying to do this, trying to incorporate single copper atoms in carbonaceous lattices, so porous carbons. And this particular approach gives you two-dimensionally polymerized carbons, graphitic carbons, with specific size of holes in them. And by ion exchange and other techniques, you can essentially introduce metal atoms in these holes. So you can put, you can see the holes in the carbon lattice. You can put 1, 2, 3, metal atoms. And we have been looking at performances, catalytic performances, whether you have one atom or you have a tandem effect when you have two atoms next to each other. So essentially controlling the positioning of atoms in lattices so that you have the ideal case where you have the minimal amount required and the maximum efficiency of the reactions that take place. So again, by microscopy, you can actually detect the positioning of individual metal atoms in these lattices. And they're clearly shown that for certain type of reactions, in CO2 reduction, the selectivity is the most challenging. And in this particular case, the CO2 to methane reduction, this type of catalyst seems to work very well. Now, before I go to the final section, I also want to mention the impact of defects. So defects are everywhere. Thermodynamically, defects are stable. But defects are interesting, particularly from graphitic structures. The whole revolution, nano-carbon revolution that I mentioned came about because defects are getting incorporated into the hexagonal graphitic network. That's why you can create fullerenes, right? You have topological defects. That's how you take a flat sheet of graphene and curve it into a ball. You need these 5-member defects. So there's also been a lot of experiments in literature reported years ago suggesting that you can actually put 1, 2, 3, 4, 5, these 5-membered defects in 6-membered hexagonal lattice of graphene, and you can create all these beautiful morphologies of graphite. In fact, this particular paper that was published in 1997 shows that you can really mass produce these type of conical shapes or flat graphitic sheets from oil and gas industry, the waste of oil and gas industry. Again, there was no real application found at that point of time. But recently, when we were looking at various types of carbons for sodium-ion batteries, because you need these hard carbons, the graphitic carbon doesn't really help. This particular structure seems to work extremely well, because one of the problems with the hard carbons, which has carbon plus another heterogeneous elements, is the cycling stability, right? Because there is reactions occurring at these sites where there is non-carbons. But these graphitic cones, they are pure carbons, but their morphologies are different, and they seem to work extremely well for the sodium intercalation and deintercalation. So again, having these engineered defects in structures could give you opportunities to explore interesting applications like energy storage. Now, finally, let me mention about this 3D printing, or the printing approach to build structures, complexity, right? So this is, again, some theoretical predictions on pure carbons. And people have, again, done a lot of work in theory suggesting that the complex carbons that you can create, possibly create, can have amazing properties. So people have predicted the emergence of magnetism in carbons if you have the right combination of positive and negative curvatures in carbons. By combining nanotubes, or graphene and nanotubes, people have predicted all kinds of interesting carbon, highly electrically conducting, and so on and so forth. Now, the question is, how do you really build these structures? If you create a porous carbons by templated approaches, which is the most common way to do it, you don't really get periodicity. You cannot control. You basically get what you have in the template. So there has to be some bottom-up approach to create these type of architectures, and there are no tools available actually to do this, right? Of course, 3D printing is a great opportunity to create complex architectures, but not to the scale that you're talking about. In this particular structure, in order to get these emergent properties, you need to have nanoscale curvatures and so on, right? 3D printing can create these, but you cannot create the scale that you require. So that's an interesting question. How far can 3D printing go, right? And in the recent times, in the last 5 years or so, there's been lots of developments in this two-photon polymerization approach of creating, 3D printed structures. You basically take a polymer precursor and polymerize it using lasers, and you can actually get resolutions that are sub-micron. Right, so this is one paper that we published a few years ago on silicon dioxide, and using the right precursors, we were able to print very complex structures similar to the ones that you saw for the carbons, again with about 200 nanometer resolution, which is really very, very good, right? Again, the last year or so, several papers have come out from different groups suggesting you can make these nanophotonic devices using the same approach. You can create oxides like titanium oxide, which have really amazing properties optically. So, we were very interested in thinking whether you can do carbon materials printed in the same way, right? The question I was asking some of the students is, can you actually print a carbon nanotube, right? That will be a revolutionary thing if you can actually do that, right? Because then you can do exactly what you want. We haven't been able to print a carbon nanotube, but we have been able to print some carbon nano wires and rods that are in that range that you're talking about. Still not there yet, but 100 nanometers, 200 nanometer resolution, you can print a carbon material pretty nicely. Here are some of the structures that we have printed in very recent times. You can really create very complex carbon-based architectures using 3D printing, reaching the less than 1 micron resolution. And with further refinement and improvements, I'm sure you can get to the kind of address the questions that I was asking, whether you can really get to the nanoscale printed carbons. And then again, a significant, really interesting materials can evolve. And to finally finish my talk, I will give you one more example, which is to do with composite materials, which can be 3D printed. Now, composites are, again, that's where I started my talk. I showed you this beautiful shell structure, which is essentially a composite of polymer, organic matter, and ceramic. And here we thought about a different composite that is, again, quite widely available everywhere. Wood, right? Wood is a interesting material because it has got this hierarchical structure, starting all the way from cellulosic building blocks to fibrils to the final hierarchical complex composite structure, right? But essentially, wood is nothing but cellulose and lignin, right? The organic and inorganic, and depending on where you look, you get different compositions of cellulose and lignin. So we thought that you, if you could actually 3D print wood, that would be fascinating, right? And all you have to do is to kind of deconvolute the essential composition of wood and reconvolute, right? And that is exactly what we did. I mean, there are other people who have printed wood, but basically they were essentially taking the whole wood and then just reprinting it. Right. What we did was we started with the components, which is lignin and cellulose, and cellulose now is available in all kinds of forms. You can actually commercially buy them. And the idea was combining different types of cellulose depending on the actual microstructure of wood that you need and lignin, and then do the right rheology, which is the most important part, so that you can actually print them, right? So that specific type of ink composition was important. And finally, we were able to actually print wood directly from its elements, right? Components, which is essentially cellulose and lignin. And again, I think the creativity or the interesting part of this is not just being able to print wood, but because printing is a hierarchical process, you can introduce other things into wood when you print. Right? I could add a little bit of nanotubes and I can make a conducting wood. I'm not sure why you need a conducting wood, but certainly you can, right? Or I can create other functionalities. I can put some silver nanoparticles and create antimicrobial wood, right? So I think the power of combining techniques and understanding how you can engineer some of these materials is fascinating, and that is the essence of the kind of things that we are interested in doing, particularly from a point of view of material science. And again, you can see you can print wood to get properties that are very similar to specific types of wood. We're comparing with balsa wood in this case. All right, so that's the message that I would like to give, that many of the kind of things that we do when the scale is small is trying to play around and trying to make sense of what would be the right approach to make the right material. And many times, this rational approach of going from bottom up is complicated. And hopefully, with all the predictions that are now possible with AI, machine learning, these approaches could be much more rational. In fact, one of the things that we really want to do is to kind of get the right kind of data from one of our growth experiments, and then use AI or machine learning to modify the whole process to actually get much better quality of products. One of the challenges in many of these, as I said, is that there is a significant variability, because again, at the nanoscale, small changes in structure changes significant changes in the properties. So you get reports of all varying dispersion. And maybe with this type of right data taking, right AI help, one could optimize some of these processes. So I will stop here and thank you very much for listening.
And now I'd like to request our Dean Thies, Professor C.V. Tommy, and Dean Research, Professor Ranjit Thapa, to come and hand over the memento presentation. Yeah, I would like to request my friend Dr. Raja Pandian to give the concluding remarks.
Good afternoon, everyone. So it's my pleasure to deliver this concluding remarks of this enlightening lecture on nano-engineered materials by our distinguished speaker, Professor Ajayan. So I extend my heartfelt gratitude to the professor for his profound expertise and innovative insights into the fascinating world of nano-engineered materials. This lecture has brilliantly highlighted the remarkable advancements in nanotechnology related to carbon materials for over the last 2 decades. We are deeply grateful for his time and effort in delivering such a wonderful lecture for us. We would like to thank our President, Vice Chancellor, Registrar, and Dean Research for their continuous support and encouragement for facilitating this university distinguished lecture. Our sincere appreciation goes to our ITKM department, CLM team, communication department, and the organizing team, Professor Vinod, Dr. Pradyut, and research office team, and many others who worked behind the scenes to execute this event smoothly. To our audience, your active participation and engagement are what make events these so meaningful. As we conclude, let us carry forward this inspiration and knowledge gained today, applying them to our work and research to contribute to the evolving field of nanotechnology. Thank you.